So first let's take there are MFR reactors in series. MFR reactors in series. Okay. Means n number of CSTRs are in series. So let's take this is the first CSTR and the inlet to the CSTR is, let me take Ca0 and volumetric flow rate of the feed is mu. Okay. And in the second CSTR consequently one more CSTR I will connect and the concentration I will assume it as Ca1. Ca1. And this is volume V1 and this is volume V2. So similarly, there are n number of CSTRs and this is another CSTR which is having outlet as some CAI. Okay, CAI. Means this is ith reactor VI. Volume of the ith reactor is VI. Okay, and then and here inlet is CAI minus 1. CAI minus 1. And finally, we are having the final reactor that is nth reactor and volume of nth reactor is Vn and the outlet concentration is CAN. CAN. Okay. CAN. And then volume is volumetric flow rate is mu and it is maintained constant throughout the reactor. Okay. So for individual time constant, let me consider what is the formula for tau I, that is space time volume by volumetric flow rate. So for individual time constant, it is Vi by volumetric flow rate. Vi by volumetric, because Vi here it is n number of volumes. N number of volumes. And similarly, I will represent one more time constant, that is tau dash. So this is nothing but n number of reactors into individual time constants. Individual time constants. So that will give you the total time constant in the complete n number of reactors. Okay. So n into tau I. Or this what I can write is n into tau I we already know. What is that? Individual volume divided by volumetric flow rate. Vi by nu. Vi by nu. Correct? So this is my representation. Now I will write the material balance. Material balance around the CSTRs, n number of CSTRs. So let's take for n first reactor, that is for n is equal to 1. For the first reactor, I am going to write the material balance. Okay. So how do you write material balance for the CSTR? What I told you in the previous class. Material balance, mole balance equation. Input is equal to output plus disappearance plus accumulation. Correct. So that is in short form. Okay. So that is in short form. That is short form. But actually, the mole balance is rate of reactants into the reactor, that is input, is equal to rate of reactants out of the reactor, that is output, plus rate of disappearance plus rate of accumulation. That is what you can write complete form. But in general, in a simple form, you remember input is equal to output plus disappearance plus accumulation. Same thing you will write for CSTR here. Yesterday I have shown two ways you can write material balance for the CSTR. What is that? In terms of molar flow rates you can write, or you can write in terms of concentrations, right? So what is that in terms of molar flow rate means? It is Fa naught is equal to input is equal to this is mole per second Fa plus minus Ra into V. This is mole balance equation around 1 CSTR in terms of molar flow rates. Similarly, in terms of concentrations, if you write, so what you will get? It is volumetric flow rate into Ca naught, that is input. Even if you multiply volumetric flow rate into Ca naught, you will get mole per second only. That is rate of flow of reactants into the reactor. This is equal to volumetric flow rate into Ca1, that is for the first reactor I am writing, only for first reactor, right? Plus minus Ra into V, that is rate of disappearance, rate of disappearance, minus Ra into V, minus Ra into V. So when I rearrange this expression, what I can get? This is for first reactor, that's why I will write V1. Okay. So if I rearrange this expression, I will take out volumetric flow rate common, then you will get Ca0 minus Ca1 is equal to minus Ra into V1, minus Ra into V1. So if I rearrange this, V1 by volumetric flow rate is equal to Ca0 minus Ca1 divided by minus Ra. Correct? This is my first equation. This is my first equation. Similarly, for N2 means only this second CSTR. For second CSTR. Same thing you will write material balance, but here input is Ca1, output is Ca2. Volumetric flow rate is same, right? Volume is V2. Volume is V2. So if I write after rearranging, what I can get the expression is V2 by volumetric flow rate is equal to, it is Ca1 minus Ca, no, second reactor. After means second reactor, there will be third reactor also, right? So the outlet will be Ca2, Ca2, right? So divided by minus Ra. So it is not coming here, I will write here. V2 by volumetric flow rate is equal to Ca1 minus Ca2 divided by minus Ra. That is for second reactor. Okay. So like that, if you keep on writing, for nth reactor, what I can write? For nth reactor, nth reactor, so it is Can divided by, means here outlet concentration, right? Sorry, not Cai. Oh, okay. Hmm. Okay, so I will do some more simplification here for the nth reactor, for first reactor. So I will consider it is first order kinetics. First order kinetics. So what is the rate equation for first order kinetics? Kca, Kca power 1, right? So here I will take Kca power 1. So that is V1 by volumetric flow rate is equal to Ca0 minus Ca1 divided by K into Ca1. You are having Ca1 and Ca1 both. So take out common, do cross multiplication and rearrange the expression. Then what you will get is Ca1 by Ca0 is equal to 1 by 1 plus K tau 1 you will get. This is for the first reactor and you consider this as first equation. Okay. So instead of stopping here in terms of rate expression, so I am taking it as first order reaction and I am substituting K into Ca1. After rearranging the expression, then I will get Ca1 by Ca0 is equal to 1 by 1 plus K tau 1. Similarly, for the second reactor also, you will get Ca2 by Ca1. Ca2 by Ca1. So same as like this. And you will get 1 by 1 plus K tau 2 you will get. Tau 2 is for the second reactor, then that is your second equation. Similarly, if you write for third reactor, fourth reactor, fifth reactor, and for the nth reactor, Can by Ca0, sorry, Can by, and the inlet concentration what for nth reactor? It is Can minus 1th reactor, right? Ca, comma, n minus 1th reactor. Can minus 1th reactor, that is equal to 1 by 1 plus K tau I. K tau I. Okay, K tau I. So this is for the nth reactor, that is tau n, and this is a third equation. So now what I will do is I will multiply all the left hand side and the right hand side. So what are we are having in the left hand side? We are having Ca1 by Ca naught, that is for the first reactor, multiplied by, for the second reactor it is Ca2 by Ca1, that is second reactor, again multiplied by third reactor is Ca3 by Ca2. Like that you can keep on multiplying in the left hand side. And the final nth reactor is Can by Can minus 1. This is equal to, this is all left hand side. For n number of reactors in series we are arranging. So that's why I'm multiplying all the concentrations of the left hand side and the right hand side. So in the right hand side what we can have, 1 by 1 plus k tau I, that is for the individual reactors. So that's why I will represent as tau I in general. K tau I, that is for the first reactor, and for the second reactor it is 1 by 1 plus same k tau I only, because for the first and second I have written here 1 and 2, but now I will write it as general representation tau I, that is for the each and individual reactor, multiplied by, for the third reactor again same 1 plus k tau I, multiplied by, so on, and for the nth reactor it is 1 plus k tau I whole to the power of whole, that is 1 plus k tau I. So this is for the n number of CSTRs. So when you observe the left hand side, this Ca1 will get cancelled, Ca2 will get cancelled. So like that all the terms will get cancelled out, and even this Can minus 1 and the previous concentration will also get cancelled out. So finally you will left with only this Can and this Ca naught. Remaining all will get cancelled out because of multiplication of n number of CSTR concentrations. So then you will get Can divided by Ca naught is equal to, that is left hand side after cancellation. Then these are all, it is 1 plus k tau I k tau I. If you multiply, what you will get, 1 by 1 plus k tau I whole to the power of n number of CSTRs. This is the general expression for n number of CSTRs. N number of CSTRs. Can divided by Ca naught is equal to 1 by 1 plus k tau I whole to the power of n. You should remember this formula directly, because you cannot derive all this. For n number of CSTRs, you can arrange and do the material balance and do simplification. You cannot do it. Simply for n number of CSTRs, either it can be 3 CSTRs, 4 CSTRs, 5 CSTRs, you simply substitute n is equal to 5 for 5 CSTRs in series. And here Ca5 divided by Ca naught is equal to 1 by 1 plus k tau I. Tau I is individual, means fifth tau I. If you are doing, means it is tau 5 whole to the power of 1 by whole to the power of n, that is whole to the power of 5. So like that we can simply do the simplification. Note down up to here. Akash, Manoj, are you following? Okay. See, this is what we have started. That is MFR reactors in series, n number of MFRs in series. As you people didn't attend yesterday's class, we already solved the many number of problems on individual reactors, how the conversion, how to calculate the conversion, volume of the reactor for the first order kinetics, for the second order kinetics. So as well as for the gaseous phase reaction, how to do the calculations for the PFR, all those things that we have done yesterday. Okay. So as you already, you might have, you can see the recorded video also and you can follow it. Okay. So now today we are continuing our previous class. Is not coming up. One more person. Okay. Okay. Next. So this is what we ended up, right? CAN by CA naught is equal to 1 by 1 plus K tau I whole to the power of n, whole to the power of n. And this is equal to 1 by 1 plus K tau I. What I can write? Tau I, because I already told you that is tau dash is equal to n into tau I. N number of reactors multiplied by individual time constants, that will gives you the total time constant for n number of reactors. So I will represent in that. What I can write is, in place of tau I, what I can write? Tau dash by n I can write. Correct? Here one, in place of tau I can write tau dash by n. This is whole to the power of n. Whole to the power of n. Okay? Whole to the power of n. So I will rearrange this. I will rearrange. So this 1 plus k tau dash by n whole to the power of n, I will bring it to the left hand side. I will bring it to the left hand side. Then this CAN by CA naught, I will bring it to the right hand side. Then this will be reversed. It is CA naught by CAN. It will become CA naught by CAN. Correct? So then this implies 1 plus K tau dash by n is equal to, so this n I will bring it to the right hand side. Okay. So this will become CA naught by CAN, and this n, when it bring it to the right hand side, this will become whole to the power of 1 by n. Okay. So or else the left hand side and right hand side you divide by n in the power. So you will get here in the right hand side you will get 1 by n. Then this I can write as K tau dash by n is equal to CA naught by CAN whole to the power of 1 by n. This 1 I will bring it to the right hand side. This is whole 1 expression. CA naught by CAN whole to the power of 1 by n minus 1. Okay. So this implies K tau dash is equal to, what is tau dash here? Total time constant for n number of CSTRs. Tau dash is equal to n by k, n by k into CA naught by CAN whole to the power of 1 by n minus 1. This you should remember in terms of time constant. So previously we are having that, that is in terms of concentration for individual tau I, for individual time constant. But whereas this expression is for the time constant, overall time constant for the n number of reactors. For the n number of reactors. So tau dash is equal to n by k Ca naught by Can whole to the power of 1 by n minus 1. So this expression you should remember. This expression you should remember. So can I write in terms of conversion also? Can I write for conversions? So what I can write for conversions? If I want to write in terms of conversion, how can I modify the expression? Tau dash is equal to n by k into Ca naught by Can, that is final concentration. That you can write in terms of conversions. What you can write? Ca naught into 1 minus Xa. Can you write? Whole to the power of n, 1 by n minus 1. Right? So here in terms for the Can for the final concentration, so I have written as Ca naught into 1 minus Xa. Ca naught into 1 minus Xa. So Ca naught will get cancelled. Then you will get tau dash is equal to n by k 1 by 1 minus Xan whole to the power of 1 by n minus 1. This is the expression in terms of conversion. So no need to remember this. If you remember this expression, then you can convert into this by simply substituting Ca is equal to Ca naught into 1 minus Xa. 1 minus Xa. Okay. This is for the overall time constant for the n number of reactors. Suppose there is a reaction and some reactants will get converted into product. And for n is equal to 1, that is for the first reactor, and the conversion in that particular reaction is, it is 0.95. Let's take it is 0.95. So I am assuming, in the sense, in general, I am doing some one small exercise about n number of reactors in series. Okay. So for the first reactor, n is equal to 1, and I considered Xa is equal to 0.95. Xa is equal to 0.95. If I substitute these values in the above expression, what I can get? Tau dash is equal to n is 1, n by k, 1 by k. Because n is equal to 1 is the sense n is equal to number of reactors. So for the first reactor, it is 1 by k. 1 by 1 minus conversion is 0.95. Conversion is 0.95 whole to the power of 1 by 1 minus 1. Tell me what is this value? This value. Hmm? 90. Hmm. So it is nothing but k into tau dash is equal to 19 you will get. That is your first value. Means here k tau dash is the for the first reactor. For the first reactor, the value you got as 19 by taking n is equal to 1. Similarly, you take n is equal to 2 for the two reactors if you have. Only two reactors, first reactor and second reactor. And the overall conversion is also again same, that is 0.95 only, even if you take two reactors. Now tell me what is the value? In this expression, you substitute n is equal to 2 and Xa is equal to 0.95. If you have two reactors in series, two MFR reactors in series, tell me what is the value? K into tau dash value. 6.944. Similarly, for n is equal to 3, n is equal to 3. In the sense, there are three CHTRs in series. Then k into tau dash value is it is 5.14. 5.14. Okay, 5.14. See, for what kinetics we are solving this problem? What is the order of the reaction? First order reaction. This is for only first order reaction is taking place in n number of CSTRs, and this is the expression. What is that expression? Tau dash is equal to n by k into Ca naught by Can whole to the power of 1 by n minus 1. This you should remember for the first order kinetics. And by taking n for first, if you have only one single CSTR, by taking conversion as 0.95, you got the value of k tau dash as 19. Similarly, for two CHRs, if you have series, then you got k tau dash value as 6.944. Similarly, if you have three CHRs in series, you got the value as k tau dash as 5.14. Okay. So now let's take for the fourth reactor. N is equal to 4. K tau dash value is, I will write the value directly, that is 4.45. 4.45. Similarly, if you take n is equal to 6, six CSTRs are in series. In that case, k tau dash value is 3.88. 3.88. Okay. So I will write for the remaining three also. What are the values you got for the remaining three? For the three CSTRs. So I will write here in general. Okay, let's see. For n is equal to 1, how much you got? For n is equal to 1, 19. 19. N is equal to 2, you have 6.944. N is equal to 3, 5.14. See, are the values are decreasing here? As the number of CSTRs are increasing, the k tau dash value is increasing, correct? So for n is equal to 4, it is k tau dash is 4.45. For n is equal to 6, k tau dash value is 3.88. Means the value is keep on decreasing. Okay, let it be there here. This is about n number of CSTRs in series. Dash 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 n number of CSTRs. For n number of CSTRs, you got the k tau dash value is like this. The trend of this k tau dash is like this. Okay, fine. For the same thing, I will do for PFR. For PFR. So what are the conditions that I have considered in the previous case? Rate of reaction is first order and conversion is 0.95. Same conversion I will take here also. Okay. Then what is the performance equation for the PFR? I told you yesterday. What is the performance equation? General performance equation for PFR.
Tau by Ca naught equal to summation of 0 to xa dxa by r.
You tell.
K naught integral 0 to xa dxa by
Sorry, that is the performance equation.
Integral. Okay.
Okay. So it is performance equation for the PFR for the performance general performance equation is tau is equal to Ca naught integral 0 to xa. It is dxa by minus Ra. Correct. So this is equal to Ca naught integral 0 to xa dxa by what is the rate of reaction? First order kinetics I considered, right? It is k into Ca. K into Ca. So this is equal to Ca naught Integral 0 to xa dxa by k into Ca naught in terms of conversions, what I can write? Ca naught into 1 minus xa. Ca naught will get cancelled. Then this is equal to, you will get 1 by k. Then what is the integral of 1 by 1 minus xa? Minus ln of, very good, ln of 1 minus xa. 1 minus xa. Here in the left hand side you have tau. Okay. So this is the general expression for the PFR. So this k, I will bring it here. K tau is equal to minus ln of 1 minus xa you will get. But here the integral term we consider for the 95% conversion. For 95% conversion, if you substitute, tell me what is the value of k tau?
.995.
2.995. This is the value for the PFR, for the first order kinetics. For a single PFR, not n number of PFRs. For a single PFR, by considering conversion as 0.95, your value of k tau, because tau here, time constant, it represents volume, because it is equal to volume by volumetric flow rate. This k tau, you will give k value. Okay, some k value if you substitute, it will be constant for all the values, either for n number of CSTRs or the PFR, k value is not going to change. So there will be some constant volume. So from this you can calculate volume. Let's say volume you can calculate from this tau. Okay. So for a single PFR, you got the k tau value as 2.995. So what about CSTR if you see? CSTR. If you take only single CSTR, k tau dash value is how much? For the fun reactor, 19. So is it very high or very less? Very high. If it is very high means what it represents? What is the effect on volume? Volume of the reactor?
Increase.
Very high. Even volume of reactor is also very high in CSTR because tau dash is directly proportional to volume. And this value 19 is very high when compared to value that what we got for PFR. PFR volume is very less, whereas CSTR volume is very high. See, for a particular conversion, 95% conversion, okay, for particular 95% conversion, the volume required in PFR is less than the volume required for CSTR. This is a general statement. See what I did numerically, I am showing, I am proving, saying that for a particular conversion, volume required in PFR is less than the volume required for CSTR. Based on k tau dash values, I am telling. For the first order reaction, k tau dash is equal to 19, and whereas for k tau for the PFR is 2.95. Based on this, I am telling volume required for PFR is less than volume required for MFR. Correct? See, then I did in some more step. One more step I did. What I did? I took two CSTRs in series. What I got tau the k tau dash 6.99944. So still does it match to the one single PFR? No. Even single PFR is less than 2 CSTR volumes. Then take 3 CSTRs in series. Does it match with the single PFR? No. Even 6 CSTRs, even if you take 3.88, that is also not matched with single PFR. Means, in the sense, here the universal truth is, if you arrange n number of CSTRs, n is equal to infinity. N number of CSTRs, if you arrange this k tau dash, it may come very closer to the value of PFR, that is 2.9 approximately. You may get when you arrange n number of CSTRs for a particular 95% conversion, the volume required for PFR is less than volume required for CSTR. That is the importance of PFR. PFR is more superior in some of the reactions.